All right, good morning, welcome back. Happy Monday. Today is April 11th. We are covering a brand new topic today called series, and in particular, we're going to do something called geometric series. And whether we know what a series is or not right at this particular moment, I will just point out that series is going to be with us for the next, I don't know, 27, 8 classes, so that this is the start of a long module on this brand new topic called series. Project number 7 is officially assigned. Go ahead and grab one from your table. Everybody have one of the project 7s? Okay, and that's not due until April 11th, which is a week from Wednesday. All right? Questions on the calendar? April 20 is when it's due. April 20. Other questions on the calendar? Okay, so just briefly about the tests. Everybody grab one of the test corrections rules from your table. You have one of those. Okay, so you're going to read through the process later on, but probably the thing that you're most interested in is what will the effect be on your grade. So there's a fancy formula there. It basically just says you can get back 1/3 of the points that you lost. You can get back 1/3 of the points that you lost. So just follow the directions that are here. Do you have one of these? And I want to make one small correction on this sheet. Right below the fancy formula, everybody see it says the test corrections will be due Monday? Everybody see that? Yep. Right below the fancy formula, cross off Monday, change it to Friday. This coming Friday. Right below the fancy formula, it says test corrections will be due Monday. We're changing that to Friday. Friday is the 15th, yes. Okay, so let's do it at the start of class on Friday. Everybody have that? There you go. Okay. All right. Generally the test went quite well for some people and not so well for other people. The median grade was an 83. So the middle person got an 83, and half folks did higher and half the folks did lower, right? One of the rules that's written out on the test correction sheet is that you can work with anybody you want to. So feel free to check with other people. There are several people that got something in the 90s. The highest grade was a 99. There are people in this room that know the answers to the problems on the test. So feel free to work with them, over in the math studio or whatever, right? Okay, if you have questions about your individual test, just see me individually. Okay, and then the other thing, so I'm going to make this announcement while I awkwardly stare at the back wall, and I want to make clear that the announcement I'm making has nothing to do with the fact that I just handed back tests. This coming Wednesday is the last day to withdraw from any class here at GCC. If you withdraw after Wednesday, you won't be able to. It'll just end up being an F on your transcript, but if you withdraw in the next 2 days, you'll have a grade of W on your transcript. It will have no impact on your GPA with a W, but an F counts against you in your GPA. Again, I'm not announcing for anybody in this particular class. If I wanted to talk to you, it says on your test, hey, let's talk. But if you are considering dropping from any class at all, you should talk to your teacher, talk to your advisor. If it's this class, certainly you should talk to me. Any questions on that?
If you have like scholarships or something that require you to have a certain amount of credits, is dropping a class that credit scholarship?
So you should talk to financial aid for that question. Yeah, financial aid is very complicated, and they've told us to just send any questions like that to them. So talk to them specifically in the next 2 days, because end of the working day on Wednesday is the last day to withdraw. Other questions? Okay. All right, so let's start here on the top of page 11 with our daily summary. In this class, we learn about series of numbers. Number 1 is our definition. A series is the sum of a sequence of numbers. So for example, the list of numbers separated by commas, 1, half, 1/3, 1/4, that is a sequence, and we talked about sequences last class. It's just a list. But if you decide you are going to add the things up in a list, 1 plus a half plus a 1/3 plus a 1/4, that is called a series, right? So a series is just a sum of a bunch of terms. The individual numbers are called terms. We're going to want to define the sum of an infinite series, which is tricky because we're trying to give meaning to adding infinitely many numbers. So what does it mean to do 1 plus a half plus a third plus a quarter forever? I can tell you what it means to add 1,000 of the terms or 1,000,000,000,000 of the terms, but what does it really mean to add them forever? So here's our definition. We're going to define the infinite series to be the limit of a sequence of something called partial sums. So for example, the first term in this sequence is 1, and we're going to use S. We used it for sequence last time. We're going to do, what are we going to do? Still sequence here. Capital S. I'm going to call it P for partial sum. So the first partial sum is just the number 1. The second partial sum is the sum of the first two numbers, 1 and a half, which is 3 halves. The third partial sum is just the sum of the first 3 numbers. Help me out here. 3, 6, is that 9 over 6? I can't do this when it's not next to each other. 3 halves and 1/3. Is it 9? No, 9. 11, 6. Yeah. Okay. So that is the third partial sum. So we're just adding them up, but we are now thinking of these new numbers as being a list of numbers, a sequence of numbers. 1, 3 halves, 11, 6 is just a list of numbers. And I know what it means to say whether or not a list of numbers converges, right? If that list of numbers hones in on a single number as I go out forever, then we would say that list of numbers, that sequence, converges, right? Well, whatever that thing is, if it converges to some finite number here, then we're going to say that's the value of this infinite sum, okay? So we're going to convert any infinite sum into just a list of corresponding terms that we call the partial sums. Okay, so let's see one of these guys in action. Number 4. I drink 1 cup of coffee containing 100 milligrams of caffeine every morning. It is known that after 24 hours, about 6% of the caffeine is still in the body. What quantity is in the body right after I drink my coffee on day 7? Okay, so let's give it a shot here. I've got day 1, the moment after I drink that cup of coffee, but before any of the caffeine has been absorbed into my body, I've got 100 milligrams, right? Just at that one moment. Let's take a look at day 2. Right after I drink the cup of coffee, that's what I'm interested in. So if I've just had a cup of coffee, then I have just introduced 100 milligrams into my system. But I additionally have some caffeine from the previous day, right? How much caffeine is in my system? Is 6% of the 100 that we had up above. Now, that's just 6, but I'm actually going to write that like that, right? 6% of whatever I had at the start of the previous day. And the total is 106, but I'm actually not super interested in that number. What I'm interested in is the day 7 number. Let's go one more day here, day 3. Right after we just had our morning cup of coffee, which means I've just introduced how many? 100. But then I had 6% of whatever I had on the previous day, right? I'm going to write that in the following way. 6% of whatever I had on the previous day. And what I had on the previous day is what's written up above. And so I'm just going to copy all of this and plop it in there. 100 plus 0.06 times 100. Divide it. That thing underlined in red, again, it's 106, but if you write 106, you're going to lose the pattern that we're trying to establish here. So I'm intentionally not doing any like simplifying with all these numbers. But there's the rule. It's just 100 plus 6% of what you had at the start of yesterday. And if we distribute here, hopefully we'll see the pattern. So this is really equal to 100 plus, so I'm going to distribute the 0.06 through the parentheses. So 0.06 times 100 plus, and then when I distribute here, how can I write that? 0.06 squared times 100, yeah? And that 0.06 squared maybe is not so surprising. That's the remnants of the coffee from the first day, and it's 6% of 6% of the 100 that you drank on the first day. And I've done enough to feel like I've got a pattern here. What does that power have to do with the day that we are on? It's just one less, right? So there's our pattern. And so if we buy the pattern, then we should be able to just predict all the way out to day 7, which is the first 100 plus 0.06 times yesterday's 100 plus 0.06 squared times the day before's 100 plus, and then where do we stop this? 0.06 to the 6th times the first 100, right? It's just the power is one less. The last power is one less than the day. Okay, so we're going to type that guy into the calculator, but the graphing calculator at least has a nice little shortcut way we can do this, so let's give it a shot. Okay, so here's the shortcut way. 100, enter. A strange thing to type in. But here's the pattern. The pattern is you take 100 and you add 6% of whatever the previous answer was. That's what we wrote, yes? 100 plus 6% of yesterday. So of course this is going to be the 106. But then what do I do if I want the next number? Well, I take 100 plus 6% of that current answer, right? Well, that's what the calculator does when you hit enter. So that's at the, so start of the first day, start of the second day, start of the third day, fourth day, fifth day, sixth day, seventh day. And so if you were to type all this stuff in black, like brute force, type it all in, you would get exactly that decimal. But the graphing calculator has a nice shortcut way to do that. By the way, was this an explicit thing that we just used the calculator for, or was that more of a recursive way to calculate this number? Recursive, because it relies on the previous number, right, which relied on the number before that. Super. So there's our answer. We can write all that out here, which is roughly 106.3829784. Fair enough. And then the question that's kind of covered by the calculator says, what happens to the level of caffeine in the body in the long run? Like if you just keep drinking 100 milligrams every day, I mean, certainly your caffeine level is going to go up, but the question is, does it go up without bound? Like, will you eventually have 200 milligrams in your system and 1,000 milligrams in your system and 1 trillion milligrams in your system? And if we look at those numbers, are they going up? Yes, but it sure feels like we are honing in on something and we're going to get there pretty soon, right? Like they are not going up. There's not a big difference between the last two numbers here. 10, 100,000, 10,000, 100,000, millionth. There's like a 5 millionth difference from one day to the next, 5 millionth of a milligram. And so let's see, day 8, day 9, day 10. Well, okay, so now my calculator can't tell them apart anymore. And so the long run is whatever that number is. Maybe there's a nice fraction way to write that. You know, I think if I had more digits, I would see they were still different by a little bit, still a little bit bigger every day than the previous. And we'll come up with a formula that will allow us to get that. But hey, surprise, we can add infinitely many positive numbers. That's what this black list is heading us towards. Infinitely many positive numbers and still get something finite. It's definitely never going to be more than 107. Okay, so coming back here to number 6, caffeine problem is an example of a geometric series, which is a series of this form, a plus ax squared plus ax cubed plus etc. What was the a in our black example here? 100. And in every example, see that a there has 100. Every term has 100. And x is the thing that you are multiplying by to get to the next term. What are we multiplying by? 0.06 to get to this guy, and then 0.06 to get to, not 0.06 squared, right? It's just another 0.06, and then another 0.06 to get to the next term. And so geometric series is just a series where you keep multiplying by the same number to get to the next term. In this case, it's a 0.06. It says the first term is a. In our example, it was 100. And the constant multiplier, also called the common ratio, is x. It was 0.06. Okay, number 7 says geometric series can be finite. Now I actually made a little typo in the notes. You guys have an Sn minus 1 written there. Just cross off the minus 1. It should have just said Sn. And while you're at it, do the same thing in the next line. They should both be Sn's instead of Sn minus 1s. Okay, so here is a finite geometric series where it just has a definite ending point, like 7 terms into this list. In this case, the sum can be found using this fancy formula. You take a, that was the first term, you multiply it by 1 minus x, that's the common ratio, 0.06 in our case, to the n. It says n is the number of terms. The exponent is the number of terms. And you divide it by 1 minus x, again, x is that common ratio. Let's just see what happens if we try this fancy new formula on the caffeine example. So let's see, I guess we found the 7th term, right? 7th term was the caffeine example. Even though the highest power was how much? 6. But it's always 1 less than the term that you're on. So copying this formula, a is how much in our example? 100. 1 minus x is the common ratio, 0.06. Raised to a certain power. The power is the number of terms, 7. It's probably also the same as this number over here, but that's not as important to me as knowing it's the number of terms. Divided by 1 minus x, 0.06. That's our ratio there. Okay, let's just see what the calculator has to say about that. So 100 parentheses 1 minus 0.06 to the 7 divided by 1 minus 0.06. There you go. That's what we got, right? The top number on the calculator was the last one before I went to days 8, 9, and 10. And that right there, is that a recursive or an explicit way to do that problem? That's explicit, right? We didn't need the first 6 terms to get the sum of all 7. That's a pretty fancy formula. You could find the sum of the first 7 or the first 8 or the first 800. And if you felt like it, you could take this green thing and reduce it as a fraction, like get a simple fraction version of this thing, which would be more accurate than just whatever the calculator is telling us here. Okay, so in number 7 here, it says that I have trouble memorizing the formula. I guess I do. The tricky part for me is just knowing the power. Power is always the number of terms. I was planning on deriving the formula, but I think we're going to skip that for right now. And if you want to see where that fancy formula comes from, I can show it to you. It's like a 2-minute thing, but we're not going to do it together. So let's move on to number 8. So a chessboard is an 8 by 8 square. We're going to place 1 penny on the first square, 2 on the next square, 4 on the next one, 8 on the next one, and every time, what are we doing to the number of pennies? To get doubling, right? So it's just always double whatever you put on the previous square. I want to know the total value of all the money on the chessboard, meaning all the way from the first square to the opposite corner square. All right, let's give this a shot. So if we're doing this here in terms of cents, 1 on the first, 2 on the second, then 4, then 8, yeah? What I need to know is what's on the last one. 2 to the, yeah, so first, how many squares are on the chessboard? 64. So what goes up here? 63. Let's see. This is really 2 to the first. This is really 2 to the second. This is 2 to the third. I guess if we like that pattern, that's a 2 to the 0. And so the power, that's the first term, second term, third term, fourth term. And so you can see that relationship, right? The power is 1 less than the term that you're on. And I know there are 64 squares on this board. So what's the power? 63rd is good. So that's what I'm interested in adding. Now, if you have a little bit of time on your hands, you could just type that into the calculator, but you're typing 64 things added up, right? Kind of annoying. So how about we use our fancy formula? I'll write it up here. A 1 minus x to the n over 1 minus x. A? A is the first term. Starts at 1 times 1 minus x is the common ratio. What do you keep multiplying by every time? That's a 2. Raised to the n, which is the number of terms. It's 64. It is not a copy of that 63. It is the number of terms. That's the trickiest part for me. Divided by 1 minus 2. And this is something the calculator can handle. So I'm not going to type that first one. So we go 1 minus 2 to the 64 divided by, and then that's just a negative 1 down there. Right? What are the units for that number? That's cents. So if I want dollars, divided by 100. Okay, so what's the word describing the number of dollars? We've got like thousands, millions. Can we do this? Millions would be what power? Would be a 6. Billions would be 9. Trillions, 12. What's after trillions? Quadrillions, 15. So that's like 1.8. Let's see, so 15. 16 would be tens of quadrillions. 17 would be hundreds of quadrillions. So about 200 quadrillion dollars on the chessboard. 184 quadrillion dollars. Yeah. So the fact is, we are, as a species, are really not equipped to handle exponential growth. We just can't process. Like I can imagine something doubling like 5 or 6 times, but like our brain was designed to like hide in a cave from wild bears, and exponential growth was not part of that. So we can think linearly really well, but the fact that we're surprised by this is just because we should be surprised by it. We're not equipped to deal with this. Okay. So we've got our answer there. What did we say? So this was roughly 1.84, I think. And so leaving it in pennies, it was 19. That's the total. The number of pennies on the last square was 2 to the 63. But our fancy formula adds up all the numbers in the sequence, in the series. Okay, fancy formula is good, right? We like the fancy formula, much better than typing in 64 things on the calculator. All right, coming down here, geometric series can also be infinite. It's the same list as before, a plus ax squared. A is still the first term, x is still the common multiplier. But in this case, instead of stopping after 7 days of coffee or 64 squares on the chessboard, we'll just let it go forever. Now, if you let the chessboard example go forever, what do you get? How much money will you have? Infinite. Okay, so that's easy. If you let the coffee example go forever, well, I don't know yet, but the calculator seemed to give me a decimal that looked like it was honing in on some magic number, whatever that was. So here's the idea. Suppose that we think about the coffee example as it relates up here. X to the n, and we're sending n to infinity. I'm just looking at the x to the n part for right now, because the n is the number of terms, right? And that's the only part which is different now. That's the infinity part. So in the coffee example, how much was x? Was 0.06, right? So we were looking at 0.06 to the n for bigger and bigger n's. And what is this limit equal to? It's 0, right? Because you're taking 6% of 6% of 6%. Every time it gets smaller, 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 and approaches 0, right? And so what that means is that this entire piece right here, if the x is something like 0.06, then that whole thing is going to go to 0, right? Okay, so this fancy formula actually becomes a whole lot simpler. It becomes that. A over 1 minus x. Just make sure you believe it. I mean, like, this is a copy of the other formula, but letting the x to the n go to 0, right? It's just copying everything else. What's in the parentheses becomes a 1. Don't even need to write it. We just get a over 1 minus x. So when does that thing go to 0? What kinds of numbers for x make this go to 0? Less than 1. What about negatives? Yeah, like if you had like negative 0.5, wouldn't it still go to 0? It would kind of bing, bing, bing back and forth, but it would still go to 0. And so any number between -1 and 1, that's this guy right here, gives us this formula because the x to the n part goes to 0. But if you have a number that is bigger than 1, for example, in our chessboard example, what was x? It was 2. Keep multiplying by 2. Then what's the infinite sum of all this stuff? Clearly infinity, right? Like there's no point trying to use a fancy formula for the chessboard example. So any number bigger than 1, you're going to have a list of numbers which by themselves is getting bigger. So clearly when you add these things, you're going to blow up to infinity. And the same problem happens with numbers that are less than -1. If the chessboard example had a -2, if that was the rule, first term was 1, second term would be -2, then +4, then -8, +16, -32. If you add them, you're just going all over the place, bigger and bigger oscillations. So that one's going to diverge as well. Rob? So if the value of x is between -1 and 1, then the series will converge and it's going to go to that formula. The other one, I don't even want to specify that it's going to infinity. I just want to say it's diverging because it could go to infinity, like the chessboard, or we could have this alternating bigger and bigger oscillations, which we're still going to say diverges, but I can't say it goes to infinity because it goes to infinity like every other term and minus infinity every other term. Integral of which one? Good luck. All right. So the group activities are here on the next page. Let's see how far we can get. You've got a couple of fancy new formulas, the finite one and the infinite one. I will walk around.